Hello, welcome to part 4D, our final session for week 4. And this is where everything comes together. Over the past 3 parts, we've built up 2 distinct skill sets. In parts 4A and B, you learned SQL fundamentals, how to create tables with data definition language and how to define data types and constraints, and how to query data with select statements, and how to filter with where clauses, how to sort with order by. These are practical database skills. You'll be using them constantly. Now, we just finished in part C, we shifted to health information standards. We talked about HL7 v2 and the messaging that's been around since the 80s. We talked about FHIR with its modern REST APIs and JSON resources. We talked about OpenEHR with its 2-level modeling and the U.S. regulatory framework driving adoption. These are conceptual frameworks for how healthcare data should be structured and exchanged. Well, now comes the integration. How do SQL skills and standard knowledge work together? How does the query you write today connect to the FHIR resource that gets exchanged tomorrow? How should standards awareness influence your database design from the outset? The title captures it. SQL meets healthcare standards. These aren't separate domains. They're 2 aspects of the same goal, managing healthcare data effectively. And by the end of this session, you'll see how they connect, and you'll be ready to apply both in your work. So let's get started. What are our objectives? We have 5 main objectives for week 4 that we'll finish today. First, we'll synthesize SQL fundamentals with the healthcare standards knowledge. And so this isn't just a review, it's seeing the connections between concepts that might have seemed separate when you first learned them. And second, we'll apply DDL, data definition language, and DQL, data query language concepts to standards-aware database design. When you create a table, how should your knowledge of FHIR and USCDI influence what columns you include? When you write a query, how might that data end up as a FHIR resource? And third, we'll understand how database queries support interoperability. The SQL you write isn't just for local reporting, it can feed data exchange, patient access, population health analytics. Understanding that broader context makes you a better database designer. Fourth, we'll practice integrated scenarios using XHealth. Rather than abstract examples, we'll use the database you've been working on to see where these concepts apply. And finally, fifth, we'll preview week 5, where we cover data manipulation language operations. These operations modify your data. And we'll also look at the join operations for combining tables. We'll look at EHR vendor specifics and do a little deeper dive into that USCDI. By the end of this session, you'll see week 4 as a coherent whole, not just 4 separate parts. All right, week 4 recap. What have we covered already? In 4A, we did the SQL fundamentals with the data definition language. You learned how to create a table to define new tables with columns and data types. You learned alter table to modify existing structures. You learned drop table to remove tables. You worked with data types like varchar, integer, decimal, boolean, date. You applied constraints like not null or unique or primary key, foreign key, and check. These skills let you define database structure. Then, moving on to part 4B, we covered data query language. You learned select to specify which columns to retrieve. You learned from to specify which table to query, and then you learned the where to filter the rows based on specific conditions. You worked with comparison operators, like patterns for text matching, and null handling. You learned order by to sort your results. These skills let you retrieve and analyze data. Part C covered health standards. You traced HL7's evolution from its onset in 1987 all the way up through today. And you learned about V2, segment-based messaging, that still handles 95% of healthcare communications. You explored FHIR with its resources, its REST APIs, and its JSON format. You understood OpenEHR's two-level modeling with archetypes and templates. You examined U.S. regulations, the Cures Act, the ONC Final Rule, and USCDI requirements. These frameworks tell you how healthcare data should be structured for exchange. Now we're up to Part 4D. It's about putting all this together. SQL skills plus standards knowledge equals effective healthcare database design and application. Notice we're highlighting Part 4D in the table because that's where we are. Let's see how everything connects. Section 2. Let's dive into the integration itself. This section is the heart of Part 4D, showing you how SQL and standards work together in practice. Now here's a principle I want you to internalize. Good database design reflects the standards. It anticipates interoperability from the beginning. You don't build a database first and then try to figure out how to make it interoperable. You think about standards from day one. So look at how XHealth was designed. It has standard coding columns throughout. ICD-10 for diagnoses, LOINC for laboratory tests, CPT for procedures, NDC for medications. These aren't arbitrary choices. They're the coding systems required by the USCDI, used by FHIR, and essential for all interoperability. The table structure is FHIR mappable. There's a patient table that corresponds to the patient resource, a provider's table that corresponds to the practitioners, an encounters table that maps to encounter. The conceptual alignment is intentional. The data elements align with that USCDI, with all of its requirements. If USCDI says demographics must be exchangeable, XHealth has demographic columns. If USCDI says laboratory results must be exchangeable, XHealth has a lab results table with the proper structure. So here's the key insight I want you to remember. The SQL you write today may become FHIR tomorrow. When you write a query against the diagnosis table pulling ICD-10 code and description, that data could be transformed into a FHIR condition resource for patient access or health information exchange. Thinking about that downstream use, the FHIR resource that might result, should influence how you design tables, how you name columns, and how you structure your queries. Standards awareness isn't separate from SQL work. It informs the SQL work. Let me show you the direct mapping between USCDI data classes and XHealth tables. This makes the alignment very concrete. Patient demographics. That's a USCDI data class. In XHealth, it maps to the patients table with columns for first name, last name, date of birth, gender, address fields. The USCDI requires demographic data to be exchangeable, and XHealth has it. Problems. That's the USCDI class for diagnoses and conditions. In XHealth, it maps to the diagnosis table with the ICD-10 code for the coded diagnosis, a description for the text, and is chronic to indicate chronicity. Medications map to our medications table with medication name, NDC code for the standard drug code, and dosage. They're all in there. Laboratory maps to the lab results. The LOINC code column provides the standard code. Test name is the description, and the result value holds the numeric result. And then vital signs. They're captured in the encounters table. with blood pressure, systolic, blood pressure diastolic, heart rate, temperature, weight, height, and a calculated BMI. Then there's procedures. It maps to our procedures table with CPT code and description. Encounters, of course, maps to our encounters table with encounter type, encounter date, and status. The care team maps to providers with the provider name, credentials, specialty, and NPI number. When you look at this mapping, you see that XHealth wasn't designed in isolation. Every USCDI required data class has a home. If an interoperability requirement says you must be able to exchange laboratory results, XHealth can meet that requirement because the structure is already there. Can someone tell me what USCDI data class might not be well supported by XHealth's current schema? Think about it for a minute. What's required that we might not have already covered? Give you a little hint. It can cause a sudden reaction. Yes, that's right, allergies. We don't have an allergies table, and that's something that you might want to add. All right, when we're thinking about querying for interoperability, let's look at a query designed with interoperability already in mind. This isn't just about getting data. It's about getting data in a way that supports downstream FHIR transformation. Look at this query on the slide. We're selecting diagnosis ID, ICD-10 code, description, diagnosis type, diagnosis date, is chronic, encounter ID, and patient ID from the diagnosis table joined to encounters. Think about that. Take that slowly. Go through that a couple of times. Notice the comments in the SQL code. Each selected column has a comment showing what FHIR element it maps to. These are comments in the code. The ICD-10 code maps to condition code. The description maps to condition code display. The diagnosis type maps to condition category. The diagnosis date maps to condition onset date time. The is chronic field informs condition clinical status. The encounter ID maps to condition encounter as a reference. The patient ID maps to condition subject as a reference. So this is documentation as sort of code. When someone reads this query, they know not just what data is retrieved, but it knows what that data will become. When the application layer transforms this result into a FHIR resource, the mapping is already explicit. And the join connects diagnoses to encounters to get the patient ID. We haven't formally covered joins yet. That's going to be in week 5, but I'm previewing them here because real interoperability queries almost always need data from multiple tables. A diagnosis record has an encounter ID, and the encounter record has the patient ID, and we need both. The where clause filters for ICD-10 codes starting with E11, which are type 2 diabetes diagnoses. So this is a practical example. Maybe we're extracting diabetes diagnosis for a population health program, or for a quality measure, or for a care management outreach. The key message: when you write queries that will feed interoperability use cases, think about the mapping as you write. Document it. Make the connections explicit. Let's see how multiple coding systems work together in practice. Healthcare data uses different coding systems for different purposes, and interoperability depends on using them all correctly. Suppose you're working on a diabetes care management program, and you need to identify diabetic patients, pull their hemoglobin A1C lab results. This requires 2 coding systems working together. For identifying diabetic patients, you query the diagnosis table. The ICD-10 code column contains the ICD-10 CM codes, and type 2 diabetes, all their codes start with E11. That's how ICD-10 organizes the diabetes codes. So you filter where ICD-10 code like E11%, the percent means a wildcard and it'll match any characters there in the rest of the string. So you can get all the diagnoses that are of type 2 diabetes. So that was a well-defined code table that allows us to do efficient record retrieval and searches. For pulling hemoglobin A1C results, you query the lab results table. The LOINC code column contains the LOINC codes, and hemoglobin A1C happens to have the LOINC code 4548-4. So you filter where LOINC code equals, quote, 4548-4, end quote, and you'll get the hemoglobin A1C results. These are separate queries here just for the illustration, but next week in week 5, when we learn joins, you'll combine them. You'll write a single query that finds patients with diabetes diagnoses and retrieves their hemoglobin A1C results linked through the patient ID. But the point for today is the standardized coding that makes all this possible. If Hospital A uses ICD-10 codes and Hospital B uses their own local diagnosis codes, you can't write queries that work across both. The ICD-10 and LOINC provide common vocabulary that allows the interoperability. And this connects to FHIR. When you create a FHIR condition resource for a diabetes diagnosis, the code element uses ICD-10 with the system URL. For example, the HTTP hl7.org/FHIR/SID/ICD-10-CM. So when you create a FHIR observation for a hemoglobin A1C, the code element uses LOINC with the appropriate connection addresses. The coding systems you query in SQL are the same coding systems that you use in FHIR. So let's trace the complete flow from SQL query to the FHIR resource. This is how we integrate our code. You start with the SQL query, select. You select the patient ID, first name, last name, date of birth, gender, address, city, address, state, from patients, where patient ID is 101. This query returns a single row with those column values for patient 101. It's tabular data, rows and columns, the relational model that you've been learning throughout the semester. Now, an application layer transforms that row into a FHIR patient resource. The transformation is straightforward because the data aligns. The resource type is patient. We're creating a patient resource. The ID is 101 from the patient ID column. The name element gets structured. The family field comes from last name. The given field is an array containing first name. The FHIR structures names this way to handle international naming conventions. And the gender field comes directly from the gender column, for, in this case, female. The birth date comes from date of birth. The address statement, the address element, gets structured. City becomes from address city, which in this case would be Columbia. And the state comes from the address state, which in this case would be the 2 characters SC. So you see how each column in the SQL result maps to a specific element in the FHIR resource? The structures parallel each other. The SQL query gets the data. The FHIR specification tells us how to structure it. The application layer does the transformation. And this is why standards-aware database design matters. If your database columns align with FHIR elements, transformation is straightforward. If they don't, you're going to have to write complex transformation logic. Not fun. Let's look at another example with a laboratory result, which shows a more complex structure. What is the SQL query? Well, we've got your select statement. And we're going to select those columns as listed in the code, as you see. And from, well, we're going to get them from the lab results. And to select which row we want, we give it the lab result ID. So this will retrieve a single lab result record, and it's now been transformed into a FHIR observation resource. The resource type is observation. The ID is 5001. The status is final in a complete system. So you'd have a status column to map, indicating whether this is preliminary or a final result. The code element is where it gets interesting. FHIR uses a codable concept structure for coded values. Inside, that is a coding array. Each coding has three parts. The system identifies where the code comes from, and the code will be an actual value, like in this case, the 4548-4. The display is a human-readable string, hemoglobin A1C, so you lose any confusion about what that 4548.4 is. It's not necessary. It's a double check, but it helps the casual reader be able to understand what this data is. And this structure supports interoperability. Any retrieving system can look at the system URI and know this is LOINC code. They can process the code value. They can display the string to users. And in this case, the value quantity holds a result of 7.2%. The subject element references the patient, like in this case, patient 101. And this is how FHIR resources link to each other through references that specify the resource type and the ID. So let's look how our lab results table columns map. The LOINC code becomes code.coding.code. Test name becomes code.coding.display. Result value becomes value quantity.value. And result unit becomes value quantity.unit. Patient ID becomes subject reference. Very straightforward. The database design anticipated this transformation, so the columns align with their FHIR elements, and that is what you call standards-aware design. So let me make the business case for standards-aware database design and SQL practices. Easier integration. When you use standard codes like ICD-10 and LOINC, automated mapping becomes possible. Your diagnosis table with ICD-10 code can be automatically transformed to FHIR condition resources because the code system is known. Without standard codes, every integration requires custom mapping logic. Better data quality, like constraints, can validate against standards. You could add a check constraint that validates ICD-10 code format, and you could use foreign keys to reference a table of valid LOINC codes. The database itself enforces the coding standards. What about regulatory compliance? The USCDI alignment is built into your schema, not bolted on as an afterthought. When auditors ask, can you exchange laboratory results per the USCDI requirements? The answer is absolutely yes, because your lab results table was designed to meet those requirements. So, future-proofing? Yes. When a new requirement comes up that needs FHIR export, we're ready. You don't have to redesign your database or write complex transformation coding. The structures already align. So, finally, is there reduced manual work? Of course. There's much less custom transformation code. It means less development time, less testing, less errors, less maintenance, fewer bugs. When the structures align, transformation is straightforward. When they don't, every integration is a custom project. So, the investment in standards-aware design pays dividends throughout the system's lifetime. It's easier to build right than to fix later. Now, Section 3. Let's step back and see the big picture. What have we learned this week? This synthesis helps you understand how the pieces fit together. I want you to visualize healthcare data systems as a stack of layers. Each layer builds on the ones below and enables the ones above. At the top is the Health Information Standards layer. This includes HL 7, version 2, FHIR, OpenEHR, USCDI, and other standards. These define how data should be structured for exchange and what data must be available. Standards answer questions like, what does a patient record look like? How do I represent a diagnosis? What data classes must the system support? Below that is the database design layer, and this includes tables, relationships, constraints, and coding systems. This is where standards get implemented in concrete structures. The patient table implements the concept of a patient resource. The ICD-10 column implements the requirement for coded diagnoses. Below that is the SQL operations layer. The data definition language commands such as create, alter, drop, and define the structures. The data query language, on the other hand, their commands like select, where, order by, retrieve data. These are how we interact with the database, creating schemas and querying the data. And at the bottom, the very bottom, is the healthcare applications layer. This includes the electronic health records, patient portals, analytics dashboards, reporting tools. These are what the end users actually interact with. A clinician doesn't write SQL code. They use an application that writes SQL on their behalf. Data flows through these layers. Standards inform how you design your database. Design determines what SQL you can write. SQL powers the applications that users interact with. So it's important that you understand all four layers. That's what makes a health informatics professional effective. You can see from standards requirements down to SQL implementation and back up to user-facing applications. So let's kind of check all the skills that we need to invoke, need to utilize. And there are 8 of them here. Let's inventory them that you're adding to your repertoire moment by moment. From Part 4A, you can create tables using Create Table, specifying the columns, the appropriate data types like varchar, integer, date, decimal, boolean. Then you can apply constraints like not null or unique or primary key, foreign key, and check. You can also modify existing structures using the alter table to add or change columns. You can remove structures using drop table when needed, fortunately very rarely. Then, moving on to Part 4B, you can query data using the select and from to specify columns and tables. You can filter results using the where with the comparison operators, logical operators like patterns for text messaging and proper null handling with the is null or is not null clauses. You can sort your output using the order by clause in either ascending or descending order. From Part 4C, you understand HL7 including the version 2 segments and how FHIR resources differ with their RESTful approach, the RESTful APIs. You can conceptually map data to FHIR resource types and understand the JSON or JSONB structures. You now understand the USCDI data classes and the regulatory context driving their adoption. Then from Part 4D today, you can see how SQL and standards connect, how the queries feed FHIR resources, how database design should anticipate the needs for interoperability. That's a lot of progress in 1 week. These are foundational skills that will serve you throughout your health informatics career. So spend plenty of time going over this and be sure that you've grasped it completely. Take a moment to give yourself a reassessment of where you are. Which of these skills are you very comfortable with? Which could you spend a little bit more time reviewing to be sure that you have them? Because this is the foundation for your career. I'd like to discuss a few common pitfalls where errors trip people up and mistakes are made, so you can try to avoid them. One common problem is using equals for null comparison. You can't do that. You can't say it's equal to null. That doesn't work. That's a common SQL mistake. Never write where column equals null. It doesn't work. Null is not a value. You have to use the is null or is not null. Select asterisks in production. That's always dangerous, to select all of the columns, because you're transmitting often lots and lots of data, and a lot of times much of it is unnecessary. Your programs and your code will run much more efficiently if you specifically list the columns you want. Another common problem is missing parentheses, especially with the and or. In order to get your logical constructs with the precedence rules correct, it's important to use parentheses, extra parentheses, to know which clauses are together, and not just use the arithmetic operator precedence. It's very simple, so don't be afraid to add additional parentheses. It makes your intentions clear and prevents surprise results. Another common mistake you need to be careful about is drop table, because there's no backup. Data definition language changes are permanent. There's no undo for that command. So before dropping anything in any real production environment, make sure you've done a backup copy and that you've tested in a development environment before you go live. A mistaken drop table can destroy data that took years to accumulate, and there's no way to replace it. Another concern is ignoring coding standards. If you're storing diagnoses without ICD-10 codes or labs without LOINC codes, you're creating an interoperability nightmare. When someone needs to exchange that data, they'll have to map it to your local versions and to develop new standards. Always include the standard coding columns from the beginning. And finally, hard coding values. Hard coding values, instead of using local codes that only your system understands, using strange terminologies, makes integration reporting analyses much easier down the road if you use standard terminologies. So what are the key vocabularies for today? Well, let's review them. The data definition language, the DDL, the DQL, the data query language, the constraints, a rule that the database enforces for you so you don't have to worry about recoding and double checking values on the fly. The not null means a column must have a value. Unique means no duplicate values, so you can't have two rows that have the same value for that column. Check validates a condition. Primary key uniquely identifies rows. Foreign key references another table. And constraints maintain data integrity. Then the foreign key, a column, sometimes more than one column, that references another table's primary key. It creates a relationship between tables. The encounter ID in the diagnosis table is a foreign key referencing encounter ID column. Then going on to the FHIR resource, the fundamental unit of health data in FHIR, like patient, or observation, condition, or encounter. Each is a resource type with a defined structure, and resources can reference each other and are exchanged via the REST APIs. In OpenEHR, you've got your archetype, a maximum data model for clinical concept, contains all possible data elements for that concept. Templates then constrain archetypes for a specific use case, for a specific patient. Now the USCDI, which stands for the US Core Data for Interoperability, the standardized set of data classes and elements that certified health IT must support for exchange, it defines what data must be interoperable, not how to make it interoperable. So if any of these terms are not clear, now's a good time to ask for clarification. Go back and look them up, find out what they mean, because this is our basic vocabulary. The data definition language, the data query language, constraints, foreign keys, FHIR resources, the OpenEHR archetypes and templates, and the USCDI for interoperability. All right, so we're coming to the end now. Let's think about what we're going to do next week, a preview, as we continue to build on this firm foundation of interoperability. Next week, we're going to look at the data manipulation language operations, which we haven't talked about yet. These are the statements of insert, update, and delete. These all modify data: add, change, delete. We're going to also talk about the join operations, which join multiple tables through foreign keys to be sure that we are able to extract data from various sources that relate to a given resource. We're going to also talk a little bit about the EHR vendors, predominantly Epic, but also Cerner, Oracle, and a little bit about some others, especially OpenEHR. Then finally, we'll do a big deep dive on the USCDI for interoperability. This is the core implementation guide. So we need to be very, very familiar with that. Let's do a data manipulation language preview, how we modify data, just to give you a taste of it. We have a comment first. We're going to insert new data. Insert into patients, and you can see what the columns are. And then we list the values, and it's going to put them in the same order as you've listed those columns. So it's going to put Jane into the first name, Doe into the last name, and that date into the date of birth. Another statement type is update. Update patient's set email equals jane.doe@email.com, where the patient ID equals 101. So it will select the right record and then insert that data into that column. And then finally, the last example is the delete. All right, so who are the EHR vendors that we're going to be looking at? We're going to look very closely at Epic. This slide says it's 35% of the US market, but I think it's closer to 60 or 65% now, especially of new sales. Oracle Health used to have about 25%, but it's dropped below 20. Meditech is diminishing, and Veradigm, or Allscripts, is used more in outpatient clinics, not hospital environments. And then when we get to the USCDI deep dive, we're going to do a detailed walkthrough of the data classes. Not just listing them, but understanding what each one requires. What specific data elements are in the demographics class? What codes are required for problems? And we'll map the USCDI to FHIR profiles. The USCDI defines what data must be exchangeable, but FHIR defines how. And the US Core Implementation Guide bridges them, providing FHIR profiles that satisfy the USCDI requirements. And we'll work through some practical scenarios. What data must be exchangeable when a patient moves from one provider to another? And what about when a patient requests the records through an app? Different scenarios exercise different USCDI requirements. And we'll connect to ONC certification requirements. If you're working with a health IT vendor or evaluating EHR systems or implementing some interfaces, you need to understand what certifications are required. So by the end of week 5, the USCDI content will be clear to you. You'll have practical knowledge that's directly applicable to real healthcare IT work. So in finishing up for today, let's bring week 4 to a close and make sure that you're prepared for the busy next week. What's a summary of the key takeaways for this week? You have to understand the SQL fundamentals that provide you the foundation for healthcare data management. Whether you're building systems, or just analyzing data, or integrating applications, or supporting some new clinical operations, you need SQL skills. The create, select, where, order by commands you've learned are the powerful tools that you'll be using day in and day out. Then you've got the data definition language with the create, alter, and drop commands. These define the database structure. These commands determine what data you can store and how it's organized. So good data definition language design makes everything else far easier. Third, we get to the data query language, the select, where, and order by commands that retrieves and filters the data. These commands power reporting, analysis, decision support, and every application that presents data to the user. The health standards HL7, FHIR, and OpenEHR all facilitate interoperability. You must be familiar with these standards. And the U.S. regulations, specifically the Cures Act, the ONC Final Rule, and the USCDI. You must be familiar with all of those regulations because they mandate the standards that we have to adopt. Compliance isn't optional for health IT systems operating in the U.S. market anymore. Understanding the regulatory context is part of being a health informatics professional. XHealth demonstrates standard-aligned design. It shows how to apply principles in practice, coding system columns, FHIR mappable structures, USCDI aligned data elements. You use it as a reference for how standards-aware databases should be designed. So here's how to prepare for next week so you can hit the ground running. Please review the DDL and DQL syntax. Make sure you're comfortable with create table, including data types and constraints. Make sure select, where, and order by feel natural to you. If something's a little fuzzy, revisit the week 4 materials. Go over it again. Then practice writing select queries with where and order by. The more you practice, the more automatic it becomes. And then try writing some queries against your XHealth data. Find all patients in a certain city, or find all encounters of a certain type, or find all patients with a certain diagnosis, or a range of diagnoses. Then please read ahead a little bit on the data manipulation language, which is what we're going to do next week. Familiar yourself with the insert, update, and delete operations and their syntax. You can find documentation online or in any SQL textbook or in the Postgres SQL documentation. If you've seen the syntax before class, the concepts will stick better with you. Then you should also explore the FHIR capabilities from the vendors, like pick Epic or Oracle. Most people pick Epic, and search for their FHIR documentation. See how they implement the concepts we've discussed. This connects theory to vendor-specific reality. And then finally think about this question. How would you query related data from multiple tables? We've hinted at joins throughout this week. What queries would you want to write that require data from patients and encounters, or from diagnoses and medications? If you have these questions already in mind, it'll help when we cover those answers next week. So we're all done for this week. We're at the end of week 4, and let me give you logistical information. Office hours are available upon request. If you're getting lost or having difficulty, I'm glad to help you. But first, be sure to check the syllabus for the times and locations. If you're struggling with any concepts, email me regarding them. For example, SQL syntax questions, or standards confusion, or how concepts connect. Anything is fair game. Now, the discussion board is a good place to post questions that might benefit everyone. If you're confused about something, chances are some of your classmates may also be similarly confused. So when you post, you help others. When others post, you might learn something you didn't realize that you needed. So the next class is week 5, covering the data manipulation operations, such as insert, delete, and update, and the join operations that combines the tables. EHR vendors and their interoperability will be another topic for discussion, and what their approaches are. And we'll do a very deep dive into the USCDI. It's going to be a busy week. It's building directly upon what you've learned here, but you've packed a lot into 8 weeks. So please stay up. If you're having difficulty, let us know early. The semester ends so quickly. Make sure that you're aware of your assignments and their due dates. Check that to-do list thoroughly every week. The combination of SQL skills and standards knowledge you're developing will serve you throughout your career. The ability to design databases that anticipate interoperability and to write queries that support data exchange and to understand both the technical details and the regulatory context are all essential. That's what makes an effective health informatics professional. And I look forward to seeing you next week.